So Harlan Campbell is a principal scientist at Precision Health Economics and Outcomes Research, as well as an adjunct professor in the Department of Statistics at the University of British Columbia in Vancouver. He completed his PhD at UBC under the supervision of the second author, Paul Gustafson, who is a professor and who is head, but with a gap year, as it were, of the statistics department at UBC, and also a recipient of the gold medal of the Statistical Society of Canada. So I'm delighted to see that this paper has received a lot of interest from the community, and that's illustrated by the fact that we have no less than 4 invited discussions provided by Val Johnson and Saptati Datta. Second one is by Daniel Heck, and then Leo Held and Samuel Powell provided a discussion. And finally, Bertrand Clark wrote an invited discussion as well. And in addition, contributed discussions were received from Frank Ladd, Andres Rakar, Kenneth Rice, Alexander Lee, Udo Bohm, and Peter Grunwald, and Stefano Rizzelli and Suman Gua. So there was really a lot of interest in this particular paper. So that's why we think it's a really good, a really cool discussion sort of paper, and also a good paper for the webinar, to be honest. Apart from being a wonderful paper, of course, that's why we publish it. But it has other features that make it sort of quite suited to, I think, this type of exercise. So the plan of this webinar is to have Harlan and I think Harlan will present the paper, and that, if possible, in about 40 minutes, something like that. And then the authors of the 4 invited discussions will speak, if possible, 5 minutes each. And finally, Paul will have about 10 minutes to present the rejoinder to the discussion. During the presentation, so attendees can write questions in the Q&A section, and we'll try and put these to the speakers. If there's enough time at the end, we might have a little bit of further discussion, but I would like to try and wrap things up in about an hour and a half. So otherwise people will just start leaving, I guess. So before we continue, I just want to make you aware again that this webinar is recorded and I think also live streamed. Is that right, Tommaso? And will be made available sort of later on. All right, so Paul, I hand the floor to you. Sorry, no, Harlan, I hand the floor to you for the presentation of the paper. Can you do you have slides you want to show, perhaps?
I do. Let me share my screen here.
Okay.
Can everyone see the title page?
Yes.
Excellent. Well, before starting, thank you so much, Mark, for putting this together, and thanks to Tommaso as well for all the logistics. It's a real pleasure to get to speak to everybody and see some new faces, and also just learn a lot about all the rejoinders and the writing the rejoinder and reading all the discussant pieces. There was lots to think about, so it's been very it's been really fun. So thank you so much for putting this together. So let me see here. As Mark said, just a little bit about myself. I'm a statistician. I live in Rossland, BC, in the Kootenays in Canada. I'm currently a scientist and a methodologist in health economics and outcomes research at a consulting group here, Precision AQ. And I'm also an adjunct professor in the Department of Statistics at University of British Columbia. And research interests, I've got causal inference, evidence synthesis, equivalence testing, reproducibility, and in general, always been interested in where Bayesian inference meets frequentist inference and how that, in those types of questions. The paper that we wrote for Bayesian analysis is actually originates from a first paper that Paul and I wrote here that we got published in the American Statistician. And And I think that's a good place to start the discussion today because it really is, this was paper one, and then paper two, we'll see how it really just came from this first paper. And this was a also rather simple idea. Uh, and it concerned, well, let's see, it concerned looking at a coin flip. So a very classic example in statistics. We flip a coin a number of times, and we are interested in whether or not the coin is fair. So there's many different ways you could do this experiment. You might be willing to assume a binomial distribution for the coin flips. That's not too controversial. And then you might consider two possibilities. One, the coin is fair, so it's 50-50, and alternatively, the coin is biased in some way. These two models we could write out different priors for this. So this first prior is a point mass at 0.5% at the 50-50 mark. And we have a uniform prior otherwise for model one. And often what you'll see is people will, here's a plot of the two priors here. So you got a spike here for theta at 0.5 versus a flat line across the range from 0 to 1. And what we typically do is we could calculate a Bayes factor comparing the two models. And depending on the results of the Bayes factor, in this case, suppose we had flipped the coin 100 times and we got 60 heads out of 100. So that's a little unusual. 60 heads out of 100 coin flips. We can calculate the probability of the data under both models. We can do the division. So that's gets us a Bayes factor of 0.913. Now the Bayes factor doesn't actually tell us what our posterior odds are. To do that, we have to multiply the Bayes factor times the prior model odds. But suppose we were evenly split a priori about which model was correct. So we believed a 50-50 chance that the coin was either fair or was biased. The posterior model odds would be the 0.5 divided by 0.5 times the 0.91. It gives you 0.913. And the conclusion, therefore, is modest support for model 0, which is the coin is fair. Despite it being 60 out of 100 heads, it's still likely we're going to believe that the coin is fair. So that whole process that we just did, we could call that testing. You're testing the two models relative to one another. You might then move on to estimation. It's always important to do both, I believe. And typically what you'll see people do is they'll write down the posterior, or they'll sample from the posterior with MCMC, and they'll get a median posterior estimate and a credible interval. So here we have a median posterior estimate of 0.598. It's slightly smaller than 0.6. That's just the impact of the prior there, shrinking things towards 0.5. And we have a 95% credible interval going from, importantly here, 0.502 to 0.691. And I say importantly because this is where you see maybe a contradiction between what we've done in testing and what we see in estimation, in that the testing conclusion is support for model 0, the coin is fair, and yet the 95% credible interval here excludes 0.5, the null. So how can this be? And why is this? This has been kind of a classic example that has led to a lot of people to write things like the fact that Bayesian estimation and the Bayes factor are incompatible because they provide different answers to the same question. We see people talk about this as paradox, or a contradiction, or a mismatch between testing and credible intervals. And perhaps the most extreme, or one of the most extreme things I found here was Wagenmakers says, because of this paradoxical state of affairs, we should not, the practice of rejecting the null whenever the 95% credible interval does not include the null value is not principal, and we should stop doing that. Here we can see this is the plot from the paper where we see the prior, the likelihood, and the posterior. And it's important to know that the 95% credible interval that we used here, the 0.502 to 691, that was based entirely on the panel H here on the lower right-hand side. And that's the posterior, assuming that model 1 is correct. And that's typically what is done in practice. But that ignores the model uncertainty. And what we are going to say here is that instead of presenting that credible interval, we should present a credible interval that acknowledges the uncertainty between model 0 and model 1, because a priori, either of those models were equally likely. So the proper posterior to consider when doing estimation is the mixture posterior, which is the lower right-hand panel I here at the bottom. You see it has the spike, but it also has this curved density. And if you consider that posterior, then you get a 95% credible interval that does include 0.5, and it goes to 0.676, yeah. And so here we see that the testing result and the estimation result are not in contradiction. In fact, they are in agreement, and this kind of solves the issue. And we would argue that this is the appropriate measure of uncertainty here, this credible interval. So that was essentially what we talked about in that paper. And it was only afterwards that we realized that, wait a minute, that 95% credible interval is not really a 95% credible interval. If you do some math and you're a little more careful and you look at it carefully, it's actually a 96.4% credible interval. Because there's this point mass at 0.5, the spike, you can't quite exactly calculate the 95%. There's a little extra posterior weight in the interval. And so it's 96.4%. So it's just a curiosity. It's nothing too much to say here. At least we thought so. And then we started thinking about this more, and that's how we ended up with the article that we're talking about today, the Bayesian Analysis paper. So as a starting point for this paper, I think we're of the opinion, and it's a good place to just start, that testing and estimation should be congruent with one another. They should arrive at the same conclusion. And in order for this to be the case, the appropriate posterior to consider that acknowledges the uncertainty with regards to which of the two models is correct is the mixture density here. And you can write it out in one of two ways. You can say it's a mixture of the two posteriors that are weighted by the posterior model odds here. Or equivalently, you can write it out as in this way, where you have a prior, which is a mixture of the two model priors here. And both those are equivalent to one another. In the coin flip example, this is what you'd end up getting. And that was that panel I in the previous slides. So moving on from here, the question is, if we're going to consider this mixture posterior density going forward, what are the properties of this mixture posterior density, and how does it compare to frequentist confidence intervals? So in the paper, we can start by considering a very simple example, similar to the coin flip, but here we have two continuous models that we're comparing. One is a very narrow prior on theta, and so it's a normal with a very small variance. And alternatively, model 1 has a wide variance. So model 0, you might call this a peri-null, is what is sometimes referred to. So it's not quite, we don't think theta is exactly 0, but if theta represents an effect size, maybe the effect size is very, very small, negligibly small, versus it is a meaningful effect size in model 1. And suppose we had some data here. The data is very simple. We looked at 10 observations, and the mean of those observations is 0.52. So here on the top right now, the two priors and the mixture prior on the far right. So you can see it's got a bit of a odd shape. The posterior here from that mixture is now on the bottom right-hand panel, and it's also a slightly odd shape, but this is the posterior that properly acknowledges the uncertainty between the two models, where each model was a priori equally likely. So if we did testing with this model, and suppose we were to do a one-sided hypothesis test, where the null is that theta is less than 0, a p-value is exactly 0.05. That's why we chose this data the way we chose it. And the z value is 1.645 so that the p would be exactly 0.05. And the posterior probability that theta is less than 0 is quite a bit higher than 0.05 here. It's 0.16. That's that little sliver in the tail here, that if we could zoom in here on this posterior. If we move on to estimation and compare the 95% confidence interval, it's a one-sided confidence interval from 0 to infinity, compared to the credible interval. The credible interval here is certainly not starting at 0. It's starting at just below 0. So there's definitely some differences here, but that might be due to the small sample size. If we looked at, say, n is equal to 100 instead, the same z value, so the p-value remains the same at 0.05. Now the posterior tail, instead of, was it 16 before? Now it's at 0.8, so it's a lot closer to 0.05. That's reassuring. An estimation, the credible interval gets a lot closer to the confidence interval, but it's still quite not there. If we look, going from 10 to 100 to n is equal to 10,000, we do see that the credible interval does approach, in the end, the confidence interval at 0.05. And the posterior value here of whether theta is less than or equal to 0 approaches 0.05. So we could say that it looks like for this mixture posterior density, the Bayesian ends up agreeing with the frequentist. Here's the same plot, but we've added now this blue line here to show the posterior probability of model 0. And one interesting thing here is that it plateaus at 0.876. So regardless of how much data you collect, you're never going to be 100% sure that model 0 is the correct model. And some might argue that because of this, the Jeffreys-Lindley paradox still applies in this case, because Bayesian testing the data will inevitably select model 0, and might come into disagreement with the frequentist. But this is a little odd, because when it comes to estimation, the Bayesian credible interval will agree with the frequentist's confidence interval as they collect more and more data. So it's not exactly clear whether or not the Jeffreys-Lindley paradox here applies. And there have been differences of opinion written about this particular example. But certainly when it comes to estimation, when you're looking at credible interval to confidence interval, it certainly does not apply. And this is the plot that we put in the paper. The bottom green line is that line we saw earlier, going from 16 to 0.8 to eventually 0.5. We just thought we'd also add, instead of just comparing to whether or not theta was less than 0, which corresponding to a 95% confidence interval, what about a 90% confidence interval? That's the blue line above. and a 80% and a 70% confidence interval. And all of those credible intervals end up agreeing with the corresponding confidence intervals, regardless of the size of those. Here's the second example we present, perhaps more interesting example, in which model 0, instead of being a narrow normal, is now a spike at 0. So this is a little bit more like the coin flip example that we started off with, where you have the spike at 0 as model 0 versus a wide normal for model 1. Actually, it's a normal with variance of 1, so I suppose it's not that wide. And once again, we observe the same data here, 10 observations with a mean of 0.52. And we can calculate that posterior. We could calculate the posterior for each of the models separately. Note that the posterior under model 0 is, regardless of the data, will always just be the spike at 0, because a prior spike guarantees a posterior spike. The posterior, if we only look at model 1, is a normal that's centered near where the data is centered, but not quite, because of the prior bringing it slightly to the left. And then the panel F here on the bottom far right is this mixture posterior that we argue is the appropriate one to consider, and it's got the spike and the curve. And because of that, when you get to testing here, just like in the earlier example, the p-value here is 0.05, as we expect, and the corresponding Bayesian value is 0.03, so that's not too far off 0.05. Here, for when it comes to estimation, things are a little stranger. The confidence interval, of course, starts at 0, but the 95% credible interval doesn't exist. Just like in the coin flip example, you can't quite find an interval that has exactly 95% posterior weight. What about larger sample sizes? This might just be an effect of a small n equals 10. What happens when you get larger sample sizes? Actually, things get more and more strange as the sample sizes increase, not less and less strange. So instead of 0.3 when n is equal to 10 approaching 0.5 in asymptotia, it actually approaches 0. We get smaller and smaller values as n increases, getting further and further away from 0.05. And if we look, what else is there to say here? No, the next slide here, if we look here at the difference between these two lines, the bottom one is strictly less than 0. Theta, the posterior probability that theta is strictly less than 0, whereas the top one is less or equal to 0. You see this widening gap between the two lines, which is odd, but can be easily explained. We call this gap here the incredibility interval. And what we're saying is, for any at a given n, for a given sample size, for any alpha value within this interval, it will be impossible to determine an exact credible interval for that alpha. And as we see, as the sample size gets increasingly larger, the incredibility interval becomes increasingly wider. So it becomes more and more impossible to define precisely alpha level credible intervals as you collect more data. And this incredible interval is because of the spike in the posterior. That spike, it soaks up all of this posterior mass, and it's all concentrated on the one point, and therefore it's impossible to find those precise spots on the boundary of that point to get the exact desired alpha value. And you can see that easily if you look at the CDF there's this discontinuity in the CDF. So here's the same data example with n equals to 10 and the values of theta. And you see this big jump here, and that jump is corresponding to that same incredibility interval. And just quickly here, so far we've always talked about 0.005 as if that's some special number, but this also the same phenomenon happens if you have more extreme data, and if you're looking at say 0.005, a more strict threshold of evidence, the posterior probability here that theta is strictly less than 0 collapses now even quicker towards 0. So there's even less agreement here as the sample size increases between the Bayesian and the frequentist. And one other thing here to say is that defining that exact credible interval will be impossible for any value of n larger than 20. We talked about sorry for the barking dog. We considered one perhaps was a little slightly bizarre way that one could still get the exact size for your 95% interval. It's possibly the only way you could define it in to get that posterior probability is to do it stochastically. So it seems a little silly, but going back to this slide, if you had to decide between the interval at, say, 0.014 versus 0.739, neither of which will give you the desired size, you could flip a coin, or you would flip a weighted coin where, say, most of the time you would end up with choosing 0.014, but occasionally you would select 0.739. And then on average, over the course of many experiments, on average, the posterior probability would be correct at 95%. So that's what we're saying here, is that you would find this value gamma. That would be the weight of this hypothetical coin. And with probability gamma, you would select exactly 0. And with probability 1 minus gamma here, 4% of the time, you would select a slightly larger value than 0. And then on average, over the course of, say, your lifetime, you would have the correct posterior probability. Right, defining theta star in this way will guarantee that the posterior probability is exactly 0.05. Shout out to, I believe it was Kenneth Rice, who pointed in their comment to this reference that proposed the exact same thing. And I don't know how how you found this, but I was quite impressed that such careful attention to detail in the literature. Someone has suggested the stochastic credible interval before. All right, is it a credible interval, or is in this case a confidence interval, but the parameter is discrete? Anyways, very, very nice find, this citation. I wish we would have been able to reference it. Proposing the same idea. Of course, this is a purely theoretical curiosity here. We're not actually suggesting that people employ the stochastic credible interval, but it's just something to think about. And when you do think about this, and you think about the value of gamma, and what those values of gamma would have to be, it's interesting that as you collect more and more data, the value of gamma approaches 1 minus alpha. That's because that incredibility interval, the posterior mass on the spike will increase until it's 100%. So the interval will eventually encompass the entire interval, the entire space from 0 to 1. And then when your entire posterior is the spike, you either have to decide, is your credible interval going to include 0 or not? And if you want a posterior probability of exactly 95%, well, then the only thing to do is entirely flip a weighted coin at 95%. So basically, the data becomes meaningless here. Regardless of the data, you're going to define your credible interval to either include or exclude zero at 95% of the time. So in conclusion here, I think just two things that we want to point to is when you're considering a point null hypothesis, or equivalently when you're using a spike and slab prior, I think those are entirely equivalent points of view. Two things to consider. The first is that because of the spike, the posterior credible interval will be rather different than the frequentist confidence interval. And when you don't have the spike, we don't see this difference, right? Even in a mixture of two very different models, you'll see that agreement between the frequentist and Bayesian testing and the frequentist and Bayesian estimation. But when you do have a spike or a spike and slab prior or a point null hypothesis, there's that disagreement in both testing and estimation. And then the second point is that just this curiosity that we have to, because of the spike, that we have to acknowledge that sometimes the credible interval will simply be undefined. And it's not that all the credible intervals will be undefined. There will still be some credible intervals. It's just that because of the discontinuity in the posterior, certain specific credible intervals do not exist. So that's where I will leave it. Thank you so much.
All right. Thank you very much, Harlan, for a very engaging, very interesting presentation. So we have first discussion was by Val Johnson and Saptati Datta. I've seen Saptati in the list of participants. I'm not sure whether Val is there. Saptati, are you going to present this discussion? Let's see. Attendees. See if I still find. Or maybe the expectation was that you would carry on for longer, Harlan.
Well, there is one question I see in the chat. I could try and address that question.
Yeah, that's a good idea. It has something to do with monotonicity, I think, wasn't it? Or yeah. So if you could deal with that.
Yeah, let me just find that slide. And that's this slide right here. And I guess the first thing to say is that while we only have 6 points here along the curve, that was just for illustrative purposes. I think we've done the calculation at maybe 200 or a few hundred different points, and then we've connected the dots. So this isn't just a smoothed curve on those 6 points. This is the actual data being plotted. And the curious thing here is, or the question was about this this bump here in the red line, so that the red line, what does it represent? It represents the posterior probability that theta is less than the lower bound of a one-sided 70% confidence interval. So I'm not sure what that value is, but the 70% confident, the one-sided 70% confidence interval has a lower bound given this data here. And whatever that value is, what is the posterior probability that theta is less than that lower bound? And eventually, with enough data, it becomes 30%, so that, we would argue is showing agreement between the Bayesian and the frequentist. But at some point along the way, it wanders into more disagreement before finally settling. And That is a rather curious behavior, and the only thing I can say about that is that there is I guess along the way, if you look at the posterior curve here, yeah, you know what? I don't really know what to make of that. Perhaps others have opinions on why that is. But yeah, I thought I had something smart to say, but yeah, it's a curious phenomenon. Yeah, the impact of the prior moving things away at these small sample sizes is perhaps the only thing that can explain that. Yeah. If there are any other questions.
I think there is, Donatello posted something in the chat about uncertainty quantification. If you can have a quick look at that, and then if you know,
see that chat. Okay, let's see. Frequentist uncertainty quantification has recently been busy with the concept of post-selection inference. One may contend that computing a confidence interval after testing a point null should not be independent of the test. Do you see a parallel with the Bayesian paradox? Computing a confidence interval after a test. Right. I suppose there's a lot of parallel, and I think we've put a note on that exact idea in the rejoinder about post-selection inference. And I suppose the parallel to draw there, and I don't know, Paul, if you want to speak to this as well, is not so much that showing a confidence interval alongside or after computing the p-value is in any way biased or not proper, but only showing confidence intervals if the p-value is less than 0.05 or if you see evidence of an effect, well, that will surely give you biased confidence intervals. And maybe that's where the parallel is. Paul, do you have any?
I'll circle back to this briefly when I present the rejoinder, but yeah, we think of the interval coming out of model averaging as being a way of kind of getting out ahead of the challenge of inference after selection. So we see a strong parallel there.
Okay, so I noticed that there are also two Q&A questions, but maybe we should stick to the schedule more or less and let the discussant who was listed second in the sort of list of discussions, invited discussions, Daniel Heck, present his discussion, and then we can come back to the Val and Saptati data discussion after that, perhaps. All right. So Daniel, are you ready to perhaps to share something with us?
Yeah, sure. I just need the rights to share my screen. Now you should see it, right?
Yes, thank you.
Yeah, thank you for organizing this discussion, and also for the very thoughtful paper. My background is in psychology, so I'm concerned with applying Bayesian methods and developing new methods for psychologists and answering research questions in this area. And my discussion contribution here focuses on three aspects, which are probably rather pragmatic and concern, an applied perspective. So the first argument concerns this basic difficulty of the discontinuity of the model average posterior distribution. And the point I make that is one that's already acknowledged in the original paper, but that this new stochastic interval is really difficult to interpret because of this combination of Bayesian frequencist concepts. So on the one hand, we have the standard credible interval and interpret it as a degree of belief regarding the most plausible parameter values. But then we on top of it, we build in this asymptotic algorithm that we flip our beliefs, similar with a coin flip, and in a way that is asymptotically appropriate. But yeah, it's a very weird, difficult thing to think about this. And I think there's a very similar solution. So if one wants to stick to these types of intervals, why not do the same as one would do with discrete parameters, where we have credible sets? We cannot construct arbitrary posterior probability levels because each value of the discrete parameter has a certain posterior probability. We can only add them up in a certain ways. And we cannot achieve arbitrary probabilities in arbitrary intervals. Why not do the same with model averaged credible intervals? So just report posterior probabilities that differ from 95%. This also has another benefit because it shows readers that this level is, of course, arbitrary. Why not report 87%, 97%, whatever suits one in an application? So we go away from conventions. This is the first point. The second point is more fundamental. It concerns the question whether such model average credible intervals are, whether we should use them at all and what are limitations and possible problems with it, especially application. And I think it's problematic concerning the interpretation because there is usually a clear line between hypothesis testing and parameter estimation. For instance, in applied areas, hypothesis testing really concerns the selection of different explanations, and we just want to know which explanation is better. And only conditionally on having enough evidence that there might be an effect, then we are interested in the effect size. So I think for in applied perspectives, it's easier to separate it. Also, very often we have one-sided hypothesis, and then the question occurs, what do we do with the model averaging? Because now we have a null model, we have a one-sided model, and now we average over the one-sided posterior and the spike. And then the question occurs, what happens if in the real world the effect is exactly on the other side? Then the credible interval will be completely wrong. So it would be a good idea to have a robust inference to always include a saturated model, a model that does not make a directional hypothesis, and then to average over it. But this leads to the question, whether one should always include a saturated model in model selection, and then one has, of course, to be careful with prior selection. Also, from a pragmatic perspective, in meta-analysis, when we aggregate credible intervals across studies or confidence intervals, there are many methods which work with standard intervals, which may be based on frequentist statistics or weakly on non-informative priors, but they don't work if we use these model averaged credible intervals. And then another pragmatic perspective, usually when we have enough evidence either for the null or for the alternative, then the averaging becomes less relevant. If there's enough evidence for the null, then the parameter is close to zero. We are not very interested in the estimate. And if there's sufficient evidence that there's an effect, the interval will be practically identical to the averaged one. And so I think especially in an applied perspective, it's still easier to separate testing and estimation. So to report base factors for testing and standard credible intervals under the alternative for estimation. The third point is just a remark about a difference where model averaging is used a lot and where I think that it's much less problematic, and that concerns averaging across models with different auxiliary assumptions. So very often we have uncertainty about the model, obviously. Should we include or exclude a certain nuisance parameter or other assumptions? For instance, in regression, which covariates to include in meta-analysis, do we use a fixed or random effects model, and so on. And model averaging is used a lot in these applications and successfully, I think. But there's this big difference because all these models we average across, they assume a continuous and usually the same prior distribution for the test parameter. And so the issue doesn't appear because we don't have a point null prior in one of the models. So the issue is not relevant in these areas because all of the models are conditional on assuming that there is an effect. Yeah, that is my contribution. Thanks again to the authors for this thoughtful article, and looking forward to the next discussions.
All right, thank you, Danielle. I'm sure Paul will touch upon some of these issues in his rejoinder. I don't think we have a Saptati Datta or Val Johnson in the list, do we, Tommaso? So I think we should just continue on with the third discussion. And I think we have both discussants, or at least I've seen both discussants. Both Leo and Samuel are here. So who is going to do the honors?
Thank you, Mark. Yeah, we actually do it together.
Good.
So I will start. All right. Can you see that?
Yes.
Okay,
Excellent.
great. So yeah, many thanks to Harlan and Paul for this great paper. I think we both enjoyed it, Samuel and myself. We also like to work in statistics, looking at things from different paradigms and comparing frequentist and Bayesian perspectives. I think that's very important. Also, if you want to, sell your methods to subject scientists. So I think it's great work. And just to recap, the simple example that Harlan showed was, about maybe the simplest model you can have in statistics. You have a mean y bar and observations, and the mean of y bar is unknown theta, and of particular interest was the spike and slab prior for theta, where you have a point mass at 0 with a certain probability. And then you mix that with a normal mean 0 and some variance G1. And then the interesting findings from Harlan and Paul were that if you look at the model averaged credible interval, posterior credible interval, then actually this may not exist at some level gamma, right? And the other interesting finding was that, and that's what they call the correlate to Jeffreys-Lipney's paradox, was that there's not even asymptotically an agreement between the Bayesian credible interval and the frequentist confidence interval for a fixed p-value. So you fix the p-value and the set value, and then let n go to infinity, and actually you don't find even asymptotic agreement. Now, in our comment, we took a particular perspective, and I think the motivation in the paper, I quoted Jack Good in his paper from 1971. He actually classified Bayesians on 11 different facets and came up that actually there are 46,656 varieties of Bayesians. So they are not just the ones, that are interested in estimation, but a certain subtype of Bayesians is actually interested in prediction. And some people argue that actually prediction is what matters in statistics. I think that's also kind of the Definetti perspective. And any parameter inference is actually just an intermediate structural step to eventually calculate the predictive distribution. And you actually see this when you look at the posterior predictive distribution of a new observable Y star. Then, of course, this is just the integral of the likelihood times the posterior, right? So this is where this intermediate structural step comes in. And you find, for example, also in Bernardo Smith's book, arguments for this perspective. So when we read the paper, we thought, well, does this result by Campbell and Gustafson also impact prediction? And I hand over now to Samuel.
Hello, also from my side. As Leo said, we were interested in looking at the predictive distributions of. Sorry, I have an echo from myself. Okay. So we were interested in the predictive distributions of the spike and slab prior and also of the mixture of normal prior. And we wanted to compare them to a frequentist predictive distribution. And you can see here the usual frequentist predictive distribution for the normal mean setting discussed before. So it is also a normal distribution centered around the observed mean, and the variance is 1 over n plus 1, which is the variance of one observation. Leo, can you go on? Okay. So also the predictive distribution based on the mixture of two zero mean normals prior, which was also shown before, can be derived in closed form, and you can see it's here. So it is a mixture of two normal distributions, and the weights of these components are determined by the base factor that has also been introduced before. And can you go one further, Leo? And the spike and slab prior is now a special case of this when one of the variances of the components to G0 goes to 0. So if you would now plug in G0 as 0, you would see that the first component would be a standard normal distribution. Right. So let's look now at how this looks like in a plot. So we show here now the predictive distributions of the frequentist predictive, then the mixture of two normals with this G0 variance of that was very small, that was also used before in Harlan's presentation in yellow. And in blue, you can see now the predictive distribution based on the spike and slab prior. And yeah, we also set the data to have a p-value of exactly 5%, as was done before in the previous presentation. And as you can see, all of these distributions look very similar. The frequentist distribution is centered exactly on the observed mean, while the others are slightly shrunken towards 0. And very importantly, there is no discontinuity anymore. And so these distributions are well behaved, and we can derive a prediction interval at any level of interest that we want. So kind of the first result disappears from the paper. And now I hand again to Leo.
Right, and then the other result was this disagreement asymptotically between credible intervals and confidence intervals. So we did kind of the same with the prediction intervals. Instead of looking at, credible confidence intervals of some level, we decided just to we compare directly the whole distribution with Hellinger distance. So here you see how the Hellinger distance between the two Bayesian formulations and the frequentist predictive distribution behaves as a function of sample size. And what you see essentially is they both drop to 0. So asymptotically, actually, they both are the same as the frequentist predictive distribution. But actually, the rate is quite different. The mixture of two normals actually converges quicker to the frequentist predictive distribution than the spike and slab one. And so we were wondering, why is this actually happening? And so we were looking at mean and variance of the predictive distributions, again, as a function of sample size. And you see in the right that actually the variance at the beginning, they're quite different, but then they more or less identical here for sample size 10, 100, and so on. But there's a large difference in the mean. So that you see actually quite some difference between the predictive means of the frequentist, the mixture of normals, and the spike and slab prior. And now actually the spike and slab prior converges quicker to the limit than the other two. Right, and that's basically our comment. And to summarize, we think, this predictive perspective on the Jeffreys-Lindley's paradox brings new insight. So spike and slab predictive distribution is absolutely continuous. So we don't have this issue anymore about credible intervals which do not exist at a certain level. If you go to predictions, they do exist at any level you like. And also the other correlate in the paper disappears. So if you fix the p-value spike and slab and the mixture of normals, they both converge to the frequentist predictive distribution. And that's just a side comment on the last paper, on the last slide, that the spike and slab converges faster to the standard normal predictive distribution than the mixture of normals and the frequentist prediction. That's basically our comment, which is attached to the paper in Bayesian Analysis. And well, thank you. And thanks for the paper. And I look forward to the discussion.
All right. Thank you very much, Leo and Samuel. So we can move on swiftly to the remaining comment, because I understand that unless Val suddenly joins us, we won't have the first discussion. Is that right, Tommaso? I think that's at least my understanding of what's been going on. There's been some issues that prevented Saptati from actually giving the discussion, and I don't think Val was expecting to be here. So it's a pity, but we still have three. Yeah, it's a good thing. We had so many. We still have three invited discussions, and Bertrand is at hand to give us the last one. So please go ahead, Bertrand.
Okay. Let me get my slides on the screen. Now.
Yep, we can see
Trying
them.
to find full screen. It was there before.
It looks good to me, Bertrand?
Okay, good stuff. And let me... Okay. So that's a tough act to follow, taking that predictive perspective. I must say I'm a little bit jealous. I wish I would have thought of that. But I do have something to say. All right. Corn is yellow. Bananas are yellow. Corn is roughly cylindrical. Bananas are roughly cylindrical. You can compare corn and bananas for their nutritional value, but you would never confuse corn for bananas or bananas for corn. Just so with Bayesian and frequentist statistics. You can compare them, but they're fundamentally different and you would never confuse them. And that, in some sense, is the subtext of this paper. So first, I'd like to restate what the paper shows, maybe a bit more exactly. And then I'd like to show you two further examples. And then I'd like to offer some explanations that I think will be different from the previous speakers. So there were two key examples in this paper. In the continuous case with mean zero normal priors and two different variances, on a normal likelihood, we get a Bayes factor and it favors the skinny prior. Hold that thought. In the limiting case of the skinny prior going to a point, to our point mass, you can define credibility levels, credible intervals for all levels without splitting the point. Sorry, can't be defined without splitting the point. That is, the sampling distribution is continuous, while the posterior has an atom at the null. So for some range, Bayesian credible intervals will just not approximate a frequentist confidence interval. Now, two things that I take away from the paper are a nice rephrasing of the Jeffreys-Lindley paradox. You know, if y bar, in the normal case, stays a fixed number of SEs away from a point null, and that could be 3, it could be 4, and actually as n increases, it can slowly increase too, and you get the same result. That means the frequentist rejects. On the other hand, the posterior probability can pile up at 0, so the Bayesian accepts. So the frequentist rejects, the Bayesian accepts. This is the classical Lindley paradox, and I think it's phrased quite neatly in the paper. So we take from this that just as there is a disjunction between Bayes and frequentist testing when you have a point null, there's sort of a disjunction between Bayes and frequentist parameter estimation, again, when the prior has an atom. So let's look at two related examples. I want to look at this is a generalization of the last example I mentioned. Let's take two models. One has a unidimensional parameter space. So we'll have yi given the theta, normal theta 1, and I equals 1 and 2, so 2 data points. It's one-dimensional because we have 1 theta. Model 2 is two-dimensional. We have a theta for each y that are tied together one level up. Okay? We'll take sigma null. So in the extension of the point null versus a one-dimensional parameter, we're really testing whether theta 1 equals theta 2, or whether we have two independently varying real parameters. If we work out the Bayes factor, we get this with some work. And you can see the Bayes factor in favor of the one-dimensional model in comparison to the two-dimensional model is essentially always greater than 1. So we're always going to be led to choose the lower dimensional model. And this is kind of like the examples in the paper. It's in particular like the example where the skinny model was chosen, as well as the other, of course. Let's look at linear models. And let's use the Zellner G prior. So I've written this family of linear models in the usual way, where gamma takes about as a vector of length p is the number of declarative variables. Each gamma I equals 0 or 1, whether or not the corresponding x is in the model, usual notation, and of course epsilon is our normal 0 sigma squared identity. Here is the Zellner G prior, and I'm just using the usual prior on sigma squared, but there's our G prior. There's our G. So if I do this, and I work out the Bayes factor, and I have, but I'm actually quoting from Clyde and George, we get this expression here, where this is the usual coefficient of determination. Now, suppose that the data overwhelmingly support some value of gamma, and the corresponding R squared for that model gamma goes to 1. Then the Bayes factor for testing 0, the null model, versus any fixed other model has the property here. The Bayes factor goes to this number. Let's look at that. This is for fixed n and fixed g. So even when it is data-wise certain the model is wrong, it still gets non-zero, perhaps large posterior probability. We're always putting mass on the simplest model. So my takeaway from this is that the real issue here is sparsity. Okay? In the first example, we end up with a line, not a two-dimensional parameter. In the second, the trivial model is always viable at some posterior probability threshold, just like the skinny normal is favored, as in the Jeffreys-Lindley paradox, as stated before. And we get the same kind of sparsity because when we use shrinkage methods, because we're using the posterior mode, a Bayesian entity. My intuition here is that because the Bayesian is tying all the parameter information together in a posterior distribution that has support on the parameter space independent of the data, it's somehow dimensionally contained, right? So as data piles up, you can get sparsity. Remember, the sampling distribution is ultimately on the sample space. So sparsity seems to be a feature of Bayes, not frequentism. So the question from an applied standpoint is, do you want sparsity? If you want sparsity, you're led to Bayes. Maybe there are settings where you don't want sparsity, and I can think of some. Maybe you're led to frequentism. Now, I'm going to take a minute to express a pet peeve of mine, because I don't really believe there is a Jeffreys-Lindley paradox. I think that's inaccurate. It's the Jeffreys-Lindley property. There's no paradox. This is just how measure theoretic probability behaves. There is a paradox in testing, I think, and it's this. The frequentist optimality criterion for testing, like the Neyman-Pearson lemma, that's persuasive, it's reasonable, it's intuitive, and it doesn't work very well. The Bayesian has the whole machinery of decision theory, and that requires a lot of extra ideas and so forth. So it's not really as convincing as just looking at density ratios, but it actually works relatively well. So there's your paradox. The frequentists have a more natural optimality criterion, but their method doesn't work as well. The Bayesian has a more complicated, less convincing optimality criterion, but the methods work really well. There's your paradox. So my big question is, why are we comparing at this very detailed level, right? Bayesians use a posterior distribution on the parameter space and find probabilities of hypotheses. Frequentists use a sampling distribution on the sample space, not on the parameter space, and they have a concept of confidence. So repeated sampling rather than the prior as information. Bayesian frequentists have different optimality criteria, really different optimality criteria. We've seen this many times. And for me, the surprising bit is that these two procedures ever agree. They're so fundamentally different. And that's, so it's valid to compare them, but we don't really expect them to agree. And so my last point is, if you don't like apples and oranges comparisons, and most of the time we don't, why are we doing bananas and corn comparisons? Thank you.
Thank you very much, Bertrand. That was indeed entertaining and informative. So I'll give the floor to Paul to give us an idea of the rejoinder.
Thanks, Mark. Let me just see if I can get my slides up.
Oh, I have to.
Is that coming through?
Yep.
Excellent. Okay. So hello, everyone. And well, let me just make sure I can advance the slides. Yes, thanks to all involved here, to the discussants, to Mark and Tommaso. It's been a real privilege for Harlan and I to be involved in this discussion and webinar. I would start by saying there's an awful lot of content in the written discussions, and a lot of suggestions and things were raised, some of which we've heard about today, others not. All sorts of good ideas, particularly about the thinking more predictively so that the point masses go away. But then there are other things that we haven't, and we heard about that from Leo and Samuel, but other things in the discussions that are very interesting, and Harlan and I weren't really attuned to a priori, so we learned a lot. And I guess I also have two particular shout outs to Bertrand, one for doing some heavy lifting and trying out some of our things in more complicated models, in regression models, for instance. And then my other shout out to Bertrand would be, I'm really impressed with the imaginative way that you met your contractual obligations to the University of Nebraska and managed to get a picture of a corn cob in your slides. That's really, yes, yeah, excellent work. Okay, so maybe and actually something Leo said maybe is a good preface here. So when he was channeling IJ Good, he mentioned the 46,000 different kinds of Bayesians. Well, this came up a little bit, I think. Maybe Daniel's written and presented discussion is maybe where the most philosophical disconnection is between the kind of point of view that Harlan and I were taking, and I don't think it's a right or wrong thing. I think it's just different philosophy. And so maybe the big question is blurring the lines between testing and estimation a good thing or a bad thing? I think you can make the case either way, but we were making the case that it's a good thing. And just to hone in on that a little bit more, in the written discussion, we mentioned two things, one of which has already come up in one of the questions today. We do worry that not having agreement between testing and estimation, not having a back and forth where the intervals kind of reveal the test results. That maybe is part of the fuel for the ongoing p-value angst we have in our community and in applied science. And then also one of the questions that was raised was about there's all this work on doing inference after model selection. And it seems, I mean, we're not experts in this, but from what we've seen, it does seem quite difficult in a sense. And in a way, if you're willing to model average to get your credible intervals in the first place, you avoid all that challenge. So that's kind of our philosophical take. We have a section in the rejoinder that we call, "Is a spike and slab prior ever a good idea?" And I kind of regret titling that section that way because I don't think it's an answerable question in a way, but we made some remarks. I mean, I guess in a way, we want to use priors that we think match how the parameters come to be in the problems we approach. And we want the prior to match the parameter generating distribution, but the parameter generating distribution is sort of a mathematical abstraction, and it's a slippery concept. That said, there is a school of thought to say that no null hypotheses are ever true, and I think we have a quote in the rejoinder from Gelman about that. And so from that perspective, the spike is not so appealing. In the other direction, the spike and slab gives you this kind of clean route to having a symmetric scale of evidence where you can talk about evidence in favor or against a null in the same terms. But of course, we all know that we're, no matter what we do, we're beholden to choosing the width of the slab, and that is a well-documented challenge with hypothesis testing from a Bayesian point of view. To elaborate on a couple of the themes in the discussion, there are lots of good ideas about refinements which have good intuition behind them, but as often is the case, those refinements add to the researcher degrees of freedom. So the peri-null idea can be appealing in some contexts, but that does make you decide if the width's not 0, then width is epsilon, and you have to pick that epsilon. And then there's also the idea that you keep the true point mass spike in the spike and slab prior, but you make the slab non-local so banishing at 0 and having modes away from 0. But of course, that's more degrees of freedom to decide how far away from 0 do those modes go and how high are they. So trade-offs are there for sure. We have a section in the written rejoinder that we call reporting, and in the spirit of sensitivity analysis, certainly we are completely okay, if you like, with having answers reported based on different priors. So reporting the credible intervals, say at a 95% level, that arise from different choices of priors. But I think in a way we got into this work because we were concerned that in some applied circles, the labeling was fuzzy and it wasn't always clear which prior was producing which interval estimate. And so sure, why not report both the model averaged one and the one under the alternative? So if you like this, here's the model averaged prior, or here's the mixture prior, here's just the prior under the alternative. They give different credible intervals. Why not report both? As sensitivity analysis, we try other priors, report those. That's fine. I think it's the labeling that in a way we got into this work because we were concerned that there was fuzziness about telling readers, particularly in applied settings, what prior is driving what interval estimate. And so that's just a plea for clear reporting. A couple of other thoughts. A number of the discussants said, "Oh, no, don't ever randomize to get your answer." We agree. So in our defense, we did. There is a line in the original paper where we say we're not suggesting this as applied practice. We are suggesting this as a thought experiment. And then the other thing I'll pick up on is another one of Daniel's thoughts. And I see again pros and cons. And it links into Bertrand's comments about sparsity as well, I think. So Daniel makes an argument that model averaging is better for some kinds of parameters than others. On the other hand, if it's sort of if we're thinking about using model averaging as a way of trying to reflect the sparsity that tends to be found in nature, then maybe we want to treat all the effects the same. And so there's a difference of philosophy there. And that's all I've got in terms of summarizing our rejoinder. So thanks everyone, and onward and upward.
That's great. Thank you very much, Paul. I just noticed there are a few questions in the Q&A. I don't know whether you can see those, but there might be something, if you have any thoughts, that you could immediately sort of, respond to the people who...
I'm just taking a look here. I see the question from Daniel Schwartz, and I think that's a tough question. I don't think even Harlan and I agree on this. We're two out of the 46,000 flavors of Bayesian. I am not so bothered by using true point mass spikes in priors. Harlan's a little less keen. We did try and have that section in the rejoinder about is it ever a good idea? It's there to try and address this question. I'm not sure it's an answerable question.
I would say so. So the question is should this work be taken as another argument against the relevance of point null hypotheses? I would just say that you can still consider evidence against a point null hypothesis without having to use the spike. You could have a perfectly continuous normal prior and perfectly continuous posterior, and if your 95% credible interval excludes, say, 0, which is a point, then you can happily reject the hypothesis, the null hypothesis, that theta is equal to 0. The tricky point comes up when you want to reject the alternative. You want to accept the null hypothesis. And strictly speaking, you can only ever accept theta is equal to 0 if you put a point mass on 0 to begin with. Hopefully that was helpful.
Yeah, thank you. And any other comments on the other points that were raised there? Because there's two more by Andrei Shrakar, who was a contributed sort of discussant as well.
I see the questions. I don't have any sort of good intuitive answers off the top of my head. I'm not aware of any strategies for point nulls that don't involve a mixture of say a spike and a slab. And
Michele said he'd like to give an answer to that, I think. Do you want to speak, Michele?
No. I was just checking the question is answered online. Thanks.
Okay. Oh, so okay.
And to me, Andre's other question is again not one I have a good answer to. I think Bertrand pushed us in this direction, so we really limited ourselves to simple one parameter problems. Bertrand pushed it a bit further, going to sort of really high dimensions. That's going to be someone else's job in the future, I think.
Okay. So Nicholas Irons wants to speak. I guess we have a couple of minutes, so if Nicholas wants to, I'm happy for that to happen. You can hear
Hi,
me?
Mark. Thank you.
Hi.
Can you hear me?
Yes.
Okay. Thanks. This has been a great discussion. So from a frequentist perspective, epistemically, you never accept the null, right? And so this that agrees with what Gelman would say. There are other kind of big Bayesians like Frank Harrell, who also agrees like point null is never true, basically. one thing you can do with this model that you describe in your paper is you can compute an intrinsic Bayes factor. So basically, you train your prior, whatever priors are specified in the paper, you train those models on some portion of your data, and then you only compute a Bayes factor with respect to that new prior that's been trained on data. And what that does is it puts the null and alternative on more equal footing. And so if you do that for this model, you'll see that you get similar behavior to the frequentist test statistic, where your Bayes factor will actually plateau and level off at a certain level asymptotically, slightly favoring the alternative hypothesis with the same data that you're looking at in the paper. And so it kind of, in that sense, that testing procedure has kind of power against local alternatives, because your Bayes factor will not point to the null in any number of samples. So you'll never actually accept the null. You'll just fail to reject, essentially. And if you then try to calculate credible intervals, in some cases you'll get behavior that also makes a bit more sense, because you don't have that point mass now absorbing the majority of the posterior mass. So the point mass for the point null will go toward like 50% for this specific model you're looking at. And so you can define a 95% credible interval. Anyway, here's what your thoughts on that.
Okay, thank you very much, Nicholas. Any comments from Paul or Harlan on that?
I will just say I have not kept up with this literature. I'm old enough to remember in the mid-90s seeing some of the initial papers on intrinsic Bayes factors and getting quite excited about that being a neat idea. Just not something that I've kept up with over the years. I'm curious, do people I'll throw a question back to the room. Are they seeing any use in applied work, or is it kind of does that message need to be revived? I don't know.
All right. Any other?
And maybe I would say, if I understand correctly, the intrinsic Bayes factor has some sort of you're using some sort of out of sample predictive ability to determine, to influence the ultimate posterior. Is that correct, Nicholas?
So basically, you start off with whatever priors you've specified, but then you train each model on half of your data, say, before you actually calculate a Bayes factor. And then the Bayes factor you compute is assuming this trained prior is your prior. And what this does is it actually washes out the effect of the initial prior that you specified. So it's less sensitive to choices of hyperparameters.
Right. Well, I would just be just one thing that just came to mind is just as the spike and slab prior has this nice relationship with the Bayesian model averaging, the equivalence there. I wonder if there's any relationship there between, since you're doing this train and test with the intrinsic Bayes factor, if there's a relationship with the stacking, Bayesian stacking, where the weights there are not.
Yeah, so Gelman's stacking is just approximates a Bayes factor, and he also, he and Atari advocate for like leave one out cross validation, and that's basically the same thing. They use the log likelihood instead of the log posterior density.
Right,
Yeah,
and you get there's very nice properties there, but maybe you don't get these theoretical guarantees of shall we say coverage, for lack of a better word, or posterior Bayesian coverage necessarily, but you do get nice predictive ability. And then just because you mentioned hyperparameter, just one extra thought I had, Leo and Sam's presentation about the spike and slab gets washed away at the second level when you go to prediction. I think the same would apply if you put a spike and slab prior on a hyperparameter, say mu is a hyperparameter for theta, and the posterior of theta would also no longer have the spike, and you'd see that convergence. Just like if you have a spike and slab on theta, the posterior of y star no longer sees the spike. It's just if you hide it one level down, then it doesn't.
Makes sense.
All right. Well, is there any other sort of urgent message that somebody wants to sort of convey to the audience? Because I think we are sort of slightly dropping participants now, probably due to the fact that we've gone on for exactly an hour and a half, which is sort of what I set myself to as a limit. So I want to sort of thank all participants for being there, and thank all the people that spoke for a really stimulating and sort of pleasant kind of discussion. It's a pity we have to do this online, but it has advantages. I mean, we can reach further into sort of sort of various areas. So it's good. It's wonderful. Thank you so much, and I look forward to the next sort of webinar, and I hope I can see again a lot of you there. So thanks to all participants. Thank you. Bye-bye.
Thank you, Mark. Thank you very much.
Thank you.
Thanks,
Bye-bye.
Mark. Thanks,
Thank you.
Tommaso.
Bye.
Thanks.
Ciao.